Good day, this is Dr. Wortel with a video discussion on Chapter 6, then the first two sections. So Chapter 6 is triple integrals, so we're going to discuss triple integrals. And let me start with 6.1, which is the definition of the integral. This will be a short video, because as we will see, the definition of a triple integral is very similar to a definition of a double integral. But that is something that we will see during this video. So if you remember what we did about double integrals, is that we first looked at the simplest possible domain. So we looked at a rectangle. We're going to take a similar approach for triple integrals. We're going to look at the simplest possible region in 3 dimensions. So now we're going to integrate over regions in 3 dimensions. So we're going to denote the regions usually by E. So we're going to take the region E, which is now a rectangular box. So it means that we will denote it like this, where interval AB times the interval CD times the interval P and Q. And this means that the x-coordinate is between A and B, the y-coordinate is between C and D, and the z-coordinate is between P and Q. So this is a rectangular box, as you will see over here. Okay, so we want to integrate over this rectangular box. So let's look back on how we do things in 1 dimension. So in 1 dimension we integrate not over a box but over an interval. And then we create partitions, and how we create the partitions is we split our interval up into smaller subintervals like this. In 2 dimensions we want to integrate over a rectangle, and how we do it is we split up our rectangle into smaller rectangles. And in 3 dimensions we have the same. So in black I've tried to draw on a rectangular box. And you see that in blue I've split up the big rectangular box, the black one, into 12 smaller ones by just chopping the x-coordinates up into, in this case, 3 subintervals, the y-coordinate in 2 subintervals and the z-coordinate also in 2 subintervals, which gives me 12 smaller rectangular boxes. So I'm going to call these smaller rectangular boxes Rijk. So they're indexed by 3 indices. This is because this rectangular box is determined by a restriction on the x-coordinate, which is given by the index I, a restriction on the y-coordinate, which is given by the index j, and a restriction of the z-coordinate, which is given by the index k. This is why we have 3 subscripts over here. Furthermore, for each of, in this case, the 12 subrectangles, I just pick an arbitrary point in the box. And again, because this depends on the single rectangle, it will also depend on these 3 indices. So it will be xijk star, yijk star, zijk star. So that's just some random point in this smaller box here. I've only drawn 1 of them, but I have to actually pick 12 of them. But I've only drawn 1 for convenience. And this point can be anywhere in the small box. Also note, by the way, that in this case the rectangles are sort of similar size, but they do not have to be of similar size. But it's just easier to draw this way, so that does not have to be the case. Our goal is to define a Riemann sum, and for the Riemann sum we need the volumes of the smaller subrectangles. So we denote this by a delta, just like we had the area of a smaller rectangle in 2D. So the volume of the rectangle Rijk, well, that's easy. That's just the difference in x-coordinates times the difference in y-coordinates times the difference in z-coordinates. We also need the diameter of such a rectangle. And again, remember in 2D we took as our diameter the size of the diagonal, and now we do the same. So we have a small rectangular box. Maybe I should sketch it over here. And we're just going to take the size of the main diagonal, so from here to here. So the length of that thing, that's the diameter of my rectangular box. So again, quite similar to the 2D case. In the formula you can see that over here. Okay, now given our partition, we also want to define a norm or a size of the partition, because we want to make it smaller and smaller. And as in 2 dimensions, we're just going to take the maximum of all of the diameters of the smaller rectangles. And again, this is called the norm of the partition P. Now once we have a partition like this, and we've picked a point in every partition, vector in every partition like this. We can define the Riemann sum, which as before is we take the sum over all possible rectangles, which now are free sums because the rectangles are indexed by 3 indices. Then we just take the function value in each point, and we multiply that by the volume of each rectangle, and we call this the Riemann sum. And you see, it's just a straightforward three-dimensional generalization. All the concepts so far are a straightforward three-dimensional generalization of the two-dimensional concepts. Now let us look at the theorems that we get. Okay, so the definition of the Riemann integral, which is definition 165 in the course notes, is basically the same. So we have a function of three-dimensional, 3 variables, which has domain now a rectangular box. Then we call the function integrable. When do we call the function integral? Well, it means for every epsilon, so no matter how small the epsilon, I must be able to find a delta such that if my partition is small enough, meaning the norm of the partition has to be smaller than delta, then the Riemann sums are going to approximate the integral arbitrarily well, in this sense up to the prescribed number epsilon given as before. So again, the definition is very similar to the 2D case. If such a number I exists, then we call this number the triple integral of f over e. And we're again going to denote it in a similar way. So now we have 3 integral symbols because we're integrating over a 3-dimensional region E. We have our function, and then we have the dv. So the v stands for volume. It's just notation, and it's reminding us that we're integrating over a volume. Okay. If you recall, what we did in 2 dimensions is that we then, once we had the integral over rectangles, we could do general bounded regions. And for 3 integrals, it's exactly the same. So now we're taking an arbitrary bounded set, and bounded basically means it will be contained in a rectangular box, a finite rectangular box of this form. Now we're going to call a function integrable if, what do we do? We're going to extend the function to 0 on the whole rectangular box. So we take the function to be equal to the original function if the point was in the region E. And if it was outside, we're going to take it 0. So we're extending our function to be 0 so that it's now defined on the whole rectangular box. And in this case, we have definition 165, which tells us, gives us conditions for integrability of such a function. So if this new extended function is now integrable over the rectangular box, then the original function we will call the original function integrable. So again, let's quickly, the idea is we have our function, we extend it so that it becomes a function defined on a box, and then we know what it means to be integrable. Once again, you can show that it doesn't matter which box you take, because you have the contribution 0 is not going to, in the limit, is not going to give you any contribution in the Riemann sums. In this case, we have the triple integral, which is just equal to the integral of the extended function over our rectangle, which has been defined in 165. Again, completely analogous to the 2-dimensional situation. So the last remark is, okay, now we have this definition of integrability, but which functions are actually integrable and how do we compute them? Well, the functions that are integrable, for that we have the very nice theorem 167, which says that if E is a closed and a bounded region and my function is continuous, then it is integrable. Again, very similar as in the 2-dimensional situation, and since almost all the functions that we will consider are continuous, probably all of them, this is very sufficient for us to know that everything is integrable. The only thing that we now need to figure out is how we are actually going to integrate this, and I will explain that in the next section.